fire ants work together to create rafts that float on the water's surface. For example, a bridge with pedestrians on it can transmit vibrations, like in the famous Millennium Bridge, Wobbly Bridge, instance. While the results of direct interactions, like nudging, are of increasing interest and study, and the results of indirect interactions through mechanisms like vision are well studied, researchers are still learning about indirect mechanical interactions, for example, how two rolling balls might INFL. Physicists are using small-wheeled robots to better understand these indirect mechanical interactions, how they play a role in active matter, and how we can control them. Their findings, field-mediated locomotor dynamics on highly deformable surfaces, are recently published in the Proceedings of the National Academy of Sciences, PNAS. In the paper, led by Shenkai Li, former Ph.D. student in the School of Physics at Georgia Tech, now a Center for the Physics of Biological Function, CPBF, fellow at Princeton University, researchers illustrated that active matter on deformable surfaces can interact with others through non-contact. Co-authors include Georgia Tech School of Physics co-authors Daniel Goldman, Dunn Family Professor, Gongjia Li, Assistant Professor, and graduate student Hussein Gainai, along with Pablo Laguna and Gabriela Small, University of Texas at Austin, Yasemin Ozkan Aydin, University of Notre Dame, Jenny. The significance of this research spans from biology to general relativity. The mapping to general relativistic systems is a breakthrough in bridging together the field of general relativistic dynamics and that of active matter, Li, of Georgia Tech, explained. It opens a new window to better understand the dynamical properties in both fields. Our work is the first to introduce the view that an active matter system can be recast as a dynamical spacetime geometry, and thus gain an understanding of the system by borrowing the tools of Einstein's theory. Setting the stage, the researchers built robots that drove at a constant speed over flat, level ground. When encountering a surface with dips and curves, these robots maintained that constant speed by reorienting themselves and turning. The amount that the robot turned was a result of how steep the slope or curve was. When these robots were placed on a circular, trampoline-like surface, the researchers were able to monitor how the robots turned in response to the changing surface, because the robots created new dips in the surface as they moved, depressing it with their weight. An overhead system tracked the robots' progress across the trampoline, recording their courses. The researchers began by testing how just one robot might move across the trampoline, and found that they could construct a mathematical model to predict how the vehicle would move. By using tools from general relativity to map the orbits to the motion in a curved spacetime, they showed that one could qualitatively change the precession by making the vehicle lighter. This model explains the orbital property, how the movement of the loops, shown here in the team's video, the precession of the aphelion, depend on the initial condition and the trampoline's central depression. We were excited and amused that the paths the robot took, precessing ellipses, looked a lot like those traced by celestial bodies like Mars and explained by Einstein's theory of general relativity, said Goldman, of Georgia Tech Physics. See what happens at this point in the video. The researchers hypothesized that increasing the speed of the robots by changing the tilt of the robot's body might help mitigate the collisions they observed. After several tests with two vehicles, they were able to confirm their theory. The researchers' solution held when more robots were added to the surface, as well. Finally, the researchers used their observations to create a model for the multi-robot case. To understand how the elastic membrane deformed when multiple vehicles were present, we envisioned the membrane as many infinitesimal, connected springs forming the surface. The springs can deform when vehicles move over them, Lee, of Princeton University, explained. In the simulation created using the researchers' spring model, the two vehicles move and merge, attracting each other indirectly through the deformation of the elastic membrane beneath, sometimes resulting in collision, just like when the team placed multiple robots on a trampoline. The overall model works to guide designs of engineering schemes, like speed and tilt of the researchers' robots, to control the collective behavior of active matter on deformable surfaces, for example, whether the robots collide on the trampoline or not. From robotics to general relativity. Interdisciplinary applications for researchers using biomimicry to build robots. The team's work could help inform robotics designs that avoid or utilize aggregation. Other systems that could potentially inspire biomimicking robots include ducklings swimming after their mother. By incorporating this work on aggregation into their design, the research could also help these robots work together to collectively accomplish tasks. Researchers add that the work could also advance the understanding of general relativity. Our conventional visualization of general relativity is of marbles rolling on an elastic sheet, explained Lee, the paper's lead author. That visual demonstrates the idea that matter tells spacetime how to curve, and spacetime tells matter how to move. Since our model can create steady-state orbits, it can also overcome common issues in previous studies. With this new model, researchers have the ability to map to exact general relativity systems, including phenomena like a static black hole. Shankai Li, Tianyu Wang, Velin H. Kojawarov, James M. Robotic swimming in curved space via geometric phase. Proceedings of the National Academy of Sciences. 2022. 119, 31, doi. 10. 1073, PNAS. 2,200,924,119 Georgia Institute of Technology. Active matter. Curved spaces. Mini robots learn to swim on stretchy surfaces. Science Daily. Science Daily. The 29th of September 2022. ift.tt/5tai8qr. Retrieved September 29, 2022 from ift.tt/5tai8qr Georgia Institute of Technology. Active matter. Curved spaces. Mini robots learn to swim on stretchy surfaces. Science Daily. https://ift.tt/5tyi8qr. Accessed September 29, 2022. Thanks for watching. Please subscribe my channel for more videos.